Welcome back to Physics 142. In the last video, we learned about this idea of self-inductance. That is, that a current that circuit that has changing current can actually affect itself. All right. What we learned is that there's this idea of back EMF, that a circuit can actually produce a potential that opposes any change in its current flow. All right, and we quantify this with Faraday's law. We look at the magnetic flux going through that circuit loop, all right, and we say that the back EMF depends on how much that magnetic flux is changing. Now we realized that for a given amount of current, that means you have sort of a given amount of magnetic field. The way that we can increase this back EMF is by increasing the area. All right, the main thing that we usually think about changing to increase this is if you have a loop or a current loop that encloses more area, all right, then you're going to get more back EMF. And what we are getting into is that this actually can be a really useful phenomenon, and it's so useful that people actually create circuit elements that their main job is to create back EMF, all right, is to create this self-inductance. And so these circuit elements are things called inductors. All right, so let's define inductor here. All right, and I will say that an inductor is a circuit element. All right, it's a circuit element designed to have a specific self-inductance. All right, it's a circuit element that's designed to have a self-inductance that we know what it is. And I should mention that this is usually large, right? That usually we're trying to increase the self-inductance of a circuit by adding an inductor. All right, and so how do we do that? Well, a circuit with an inductor looks like this. All right, what we do is you draw your circuit. Like usual, maybe it has a switch in it, okay? But then what we do, the way that you draw an inductor is, the way that you make an inductor is you want to think about having a large area, and the way you do that is with many, many, many loops, right? You make many loops of wire, and that means that you have a large area for magnetic flux. And so our circuit with inductors, the little symbol for an inductor is actually just like that, all right? It's basically you take and you draw many loops, all right? So it sort of like a solenoid or something, right? Many loops of wire here, all right? You get a lot of magnetic flux through that, all right? That's the symbol for an inductor. And I don't know, maybe your circuit also has a resistor in it or something like that, all right? But this here is your inductor, all right? That's the symbol for an inductor, many loops. And well, why would I actually want to do that? All right, why do I want to know the self-inductance, and why do I want to increase the self-inductance? Well, the thing about self-inductance is it's opposing rapid changes in the circuit, right? It's taking that current change and it's making it spread out in time, over time, right? So let's write that down. So inductors oppose rapid changes in a circuit. All right, or in other words, we could say, another way of saying that is they fight to keep the current steady, right? They don't like change, right? They're resistant to change, right? The more change you have, the more they fight back. That's the job of an inductor. And this actually can be really important, right? Think surge protectors. They're all about trying to protect against large changes in current, right? We do this on power lines. Power lines have giant inductors on them with the idea that if they get struck by lightning, rather than getting a big surge in the amount of current, all right, the inductor is going to fight against that surge in current, right? It doesn't want a rapid change. It's going to sort of slow that change down, and that protects the rest of the electronics, right? So anytime you need to keep your current flow steady, you probably want to put an inductor in your circuit, all right, because its job is to oppose change, all right? It's to keep the current steady. All right, so great, we have inductors, all right? The symbol for an inductor, all right, if we talk about resistance is R, all right, inductors and inductance gets the symbol L. All right, and it would be nice if we could quantify this a little better, right? If we could actually define L a little bit quantitatively. And the way we do that is, well, we know that the back EMF, that the self-inductance depends on change in flux, right? And so, so we know it must depend on flux somehow, so let's write that down, all right? And flux depends on basically how much B field you have, all right, and your geometry, right? It's the integral of B dot dA, so it depends on B and on A, right, on your geometry, all right? But the amount of B field that you have in a circuit, well, the amount of B field that you have depends on how much current you have, right? The more B field you have, the more current you have. So what we can say is we can say that flux, right, sort of maybe a little bit more indirectly, right, but it depends basically on how much current you have and on the geometry. All right, those are the two main factors that are contributing to the flux going through this inductor. And so if we want to quantify the inductance, well, current is just current through the circuit, all right? All the sort of power of the inductor actually ends up coming in the geometry part, all right? So what we do as a matter of definition is we say that the flux through an inductor, all right, is its inductance times the current, all right? So this is actually a way of defining L, right? We could say that L is defined to be flux per unit current, all right? So in terms of units then, flux has units of Webers, all right? Current has units of amps, all right? And 1 Weber per amp actually gets a special name. That's 1 capital H, or capital H here stands for 1 Henry. All right. And so this is just saying that, that flux, all right, the sort of strength of the magnetic field, all right, depends on how much current you have. And so also our reaction is going to depend on the amount of current. Maybe to make this a little bit more specific now, all right, is, well, if we want to actually think about how much back EMF we have, okay, we want to think about how much does the potential change here. All right, let's write that down. So if we want to know what V back is, right, what our self actually change in potential, or, often V, we're talking about this as EMF, all right? So if we actually want to write down the back EMF in terms of sort of inductance here, all right, then we say, okay, that is minus d phi dt, all right, which is minus ddt of, we've just defined this L, all right, this inductance, which just basically just takes all the geometry here, right? It just is something that depends on the geometry of these circuit coils, the geometry of your inductor, all right? And it just says that flux is depending on geometry and current. So L is just telling you about your geometry. So we say, all right, ddt of L times I. Well, and if L just depends on your geometry, all right, then that's just constant. Once you've configured your wire, once you've made your circuit element, L's not going to change. So I can pull that out of the derivative here, and usually we write this as minus L times di dt, all right? So minus L di dt. Now remember, this minus sign is just saying that we're opposing the change, right? So the minus sign is all about opposing the change in current. So inductance, right? That's sort of how good you are at opposing that change, right? And di dt, that's how your current is changing. So basically, the better you are at opposing the change, the more back EMF you get, right? So higher L will give you more back EMF, and a bigger change in current will give you more back EMF. All right, so this is a little bit tricky to conceptualize. And so I would like to take a little time to have us, really think about this more deeply, and especially to think about this sign here, right? This idea of opposing the change in current. All right, what does this mean? How can we sort of understand this in more detail? So to do that, let's draw ourselves 4 circuits. All right, so I'm going to draw a circuit over here that just has a power supply and a resistor in it. Okay, so here is a circuit with a power supply and a resistor. And then let's draw 3 circuits, all right? And they're all going to look the same, but we're going to have different things going on in them, all right? So here's an inductor. I'm going to put an inductor in this circuit. And all 3 of these circuits here, we'll just do it right here. All right, all 3 of these circuits, I'm going to have an inductor in. All right, so there we go. And one more. Okay. Now, the question that I want to think about a little bit more is, let's really understand, okay, how is the potential in my circuit, all right, changing how is the potential in my circuit change depending on the fact that there's an inductor in it, all right? What's the impact of this inductor on my circuit, okay? So here's how I want to think about that is, well, normally we think in this circuit, right, we have the power supply, and the power supply is going to create some current, right? We'll have current. And the current's going to flow through here. And if we think about what happens as you go across a resistor, what we know is we go across a resistor, all right? When you have current flow across the resistor, you lose potential, right? You lose potential. All right, that means your EMF, you would say, as you went across this resistor, right? The EMF as you went across the resistor went down, right? It was negative. You lost EMF as you went across the resistor. So we know that's the case, right? Resistors take away your potential. All right. Now, next case is, let's think about, well, what if we have the same circuit, but now we have an inductor here, all right? So again, we're going to have I flow. And the first case I want to think about is, what if your current is steady? All right, what if it is steady? All right, not changing. Okay, let's move this up a little bit. Okay, if it's not changing, what's going to happen? Well, if it's not changing, mathematically, we write that as di dt equals 0, right? It's not changing, all right? Well, and if di dt is 0, then if we want to calculate sort of the potential across this inductor, all right, what's it going to be? Well, the potential across the inductor is minus L di dt, right? But di dt is 0, so that's 0, right? So you don't get any potential change. So I can have current flowing, but if that current is steady, if it's not changing, the inductor doesn't do anything, right? And so what I usually like to say is that, the inductor is happy with the fact that it's steady. It's going to act like a wire, all right? It acts like a wire, right? There's no change in the potential, right? No change in potential. Okay. All right. So that's all well and good, but then what if, maybe I start turning my power supply up a little bit, all right? So now I have my current flowing again, all right? But now I'm going to increase I, all right? So let's have I increase. Okay, we're increasing I, or I guess I write that here, I is increasing. And so that means di dt, right, the change of current with time is positive, right? It's going to be getting bigger, all right? So it's positive di dt here, positive di dt. And so if that's the case, if di dt is positive, then if we want to calculate the EMF across the inductor, right, this back EMF, that's going to be minus L di dt. And if di dt is positive, L is just a property of the inductor, it's just the geometry, so that's a positive number. All right, what you're going to get is that the EMF is negative. All right, EMF is negative, or, you know, again, we're losing potential. Right, so again, we lose potential. All right, we lose EMF here, we lose potential. The EMF is negative, all right, if you have increasing current. And so, you know, what we could say here is what I usually like to say to sort of quantify this a little bit, all right, is I say that the inductor in this case is acting like a resistor, right? It's acting like a resistor, and we have it opposes the increase in the current, right? So we have a negative change in potential. We're opposing the increase in current, right? Opposing the increase in the current, just like resistors, they oppose current, all right? Here, if it's increasing, we're opposing the increase. It's acting like a resistor. All right, final situation. And maybe you can see where this is going, right? Is now, if we have current again flowing, all right, but now we're going to decrease it, all right? So we're gonna have I decreasing. So that means di dt is going to be negative, less than 0, right? Negative. And now we're going to get, you know, if we do EMF of the inductor, right, it's going to be minus L di dt. And now we're going to have minus a minus, all right, which is going to give us positive EMF, all right? So here, actually, if you go across the inductor this way, you know, if you go with the current, all right, you're actually going to gain EMF, all right? EMF is positive when you go across an inductor, all right, if the current is decreasing, all right? So in this case, all right, in this case, we say that it's actually trying to oppose the decrease, right? So I'll write that down. It's opposing the decrease, right? It's opposing the decrease. So what does that mean? It means it's trying to actually pump more potential into the system, right? It's trying to pump more current into the system. And so we could say that it's actually acting basically like a power supply, all right? It acts like a power supply, right? It's trying to supply additional current to the system, because if the I is decreasing, it says, no, 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 I don't like that. Let me give you more current, all right? Here, if I is increasing, it says, no, 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 I don't like that. I'm going to take away current, right? Here, I decreasing, it says, that's no good. Let me give you current, right? So it's always doing the opposite of what's happening. If it's steady, it's happy. Things are good, all right? Nothing's going to change. The inductor basically doesn't do anything, all right? But as soon as you start losing current, as soon as you start gaining current, all right, the inductor says, that's not good. I'm going to act like a resistor, try to slow you down, all right? If you start losing current, the inductor also says, that's not good. Let me boost you up a little bit, all right? I'll try to give you some more current. Okay, so inductors are always doing whatever it takes to oppose the change, all right? They do not like change, all right? They are trying to always keep things as steady as possible. So hopefully this gives you a little better understanding of how all the signs work, sort of mathematically, how we can understand inductors, and also sort of conceptually how we understand inductors. So there you have it.